All right, more kinematics problems, more fun. Here is question number 3 from page 53. Okay, it says a car starts from rest and travels 5 seconds at a constant acceleration of negative 1.5 meters per second squared. It says, what is the final velocity of the car and how far does the car travel in this time interval? So, first of all, I've been reading these questions and we haven't really been processing. It says a car starts from rest. So that means it's not moving and it travels for 5 seconds. Well, that's kind of cool. With a constant acceleration that is negative. What? It's got a negative acceleration even though it started from rest? Okay, so we've done these problems. We've talked about this a lot. If it's starting from rest and it has a negative acceleration, I'm thinking it's going to be speeding up, going away from the origin in the negative direction. Just saying, just kind of something to think about. It asks what the final velocity of the car is, and then it's a double question because it also asks how far does the car travel in the time interval. So we'll get started with the first part, and then I'm sure we'll get to the second part as we go. So anyway, let's go ahead and start our graph because we're going to do this graphically first, and then we'll do it algebraically as always. Okay, so we've got our velocity over here. It says it's starting from rest, so we'll go ahead and start it from rest at v equals 0 at the time equals 0. And it's going to travel for 5 seconds. So there's my 5 seconds. And it's going to be negative, isn't it? I should have been a little bit more clever in my axes drawing. That's okay. I'll just go like this. And I'm going to have a negative slope. That means it's going to go to a negative velocity in those 5 seconds. And I don't think this has to be to any sort of scale because it's just a sketch to give us a sense of what's going on. Okay, so I'm starting off at an initial velocity of 0, and I have a negative slope because I have a negative acceleration for 5 seconds. Okay, so again, I don't know how fast it's going at the end. That's what I'm trying to figure out. So I'm trying to figure out what this value is, this final velocity. How am I going to do that? Well, I know my acceleration, and I know that that is the slope. I know in this case the run, and I'm looking for the rise. So we can do this. We know that slope is rise over run. We know the slope, that is, let me get some new colors here, negative 1.5 meters per second squared. We know that, we don't know what the rise is. That's what we're looking for, right? That change in velocity. And really what we're looking for is the final velocity because we're starting at 0, divided by our run, which was 5 seconds. Okay, so it's a pretty easy problem to figure out then, right? Because we've got 1.5 meters per second squared. To solve for v, we're going to multiply by 5. So that's going to give us a final velocity, right? Because we're starting at 0. So final velocity minus initial velocity, vf, minus 0. So that's just going to be vf, is equal to 1.5, or negative 1.5, meters per second squared times 5 seconds. We can do that. Negative 1.5 times 5 is 7.5, or negative 7.5, meters per second. And that, my friends, is the final velocity. There you go. Okay, oops. Come on there, stylus. There we are. All right, so that's the first half of the question. The second one says, how far does the car travel? Okay, well, we can do that too. I know we can. So we now know that the final velocity is negative 7.5 meters per second. And if we recall, we find how far, well, let's remember what how far means. How far means what is delta x, right? That's what we're looking for. And we find the displacement by finding the area between the curve and the axis. So this one's a little bit different because the curve is now down below. So here's my curve, here's my axis, and this right here is the area I'm looking for. Can I find the area of that triangle? Why, yes, I can, right? It's 1/2 the length times the width. So I'm just going to look at my length and look at my width. I know my length is, so this is the change in position, is equal to 1/2. Well, my length is going to be 5 seconds, and my width is going to be negative 7.5 meters per second. Is that Is that okay? Now, hold on just a second here. Oh yeah, I know why there's no negative sign. So if I multiply 1/2 times 5 times negative 7.5, that's going to get me about 19 meters. I got a negative 19. Why? Because I'm solving for displacement. I was just looking at these answers up here and I see that the answer is 19. But it's just because it says how far does the car travel. So it's really looking for a distance, not the displacement. If you give me a negative 19 on a question like this, even though it's just asking for that 19, I would never count that wrong because that's just giving me more information. So that's totally fine. So there you go. Bam, we got that done. Now, let's take a look at it algebraically too, because, we want to share the fun with everybody, no matter their preferences. And so we want to do the algebra as well. So let's go ahead and write down our givens. Here we go. All right, so it starts from rest. That's an initial velocity of 0. It travels for 5 seconds, so that's my time. It's got a constant acceleration of negative 1.5 meters per second squared. And the first part asks, what is the final velocity? So I'm going to go ahead and write VF equals question mark. I'm going to write that as like part A. And then just to remind myself that part B, delta X equals question mark, we can solve as well. All right, so we're going to go ahead and do part A. So we've got VI, VF, T, and A. So if we go back and take a look at our equations, okay, we're looking for something that doesn't have anything to do with displacement. And if you recall, that was that second equation that we had. VF is equal to VI plus A delta T. So let's go ahead and find that one. So we'll write that down. So VF equals VI plus AT, okay? So we can do some manipulation here. We're looking for VF. Oh, wait, we already have VF, so we're good to go. So that's that initial velocity is 0, so we can get rid of that. And we can just say that VF is equal to negative 1.5. Come on. 5 meters per second squared times the time, which was 5 seconds. And we get negative 7.5 meters per second, same as we had before. Okay, and again, really, it's just the same setup, just a different approach. So that's part A. Part B, now I want one little top tip here is that if you're doing it algebraically, I would strongly encourage you not to use your calculation from part A to do part B because there's other ways to do things. So in this case, I would use the initial velocity, the time, the acceleration, and the displacement. So if we take a look at that, let's look at our equation. So we're not going to include final velocity in any business here. So if you look at that, which one are we not going to include? Well, it gives us a new equation to play with too, which is fun. It's my favorite one. It's the long one. It doesn't include VF. Here we go. So we're going to take a look at this. So we'll write down Ms. Carbling's favorite kinematics equation. It is delta X is equal to VIT plus 1/2 AT squared. Why do I like it? Because it's super useful. You'll see soon. Now we're going to take a look. It's already solved for delta X, so that's super convenient. We're going to get rid of that because the initial velocity is 0, and anything times 0 is, say it with me, 0. Yeah, so there you go. So now we're just going to plug stuff in. So we've got 1/2 times negative 1.5 meters per second squared times the time squared. So that's going to be, where are we at here? That's 5 seconds, 0.0 seconds squared. And that will give us our displacement, I believe. And yeah, it gives us negative 19, just like it did before. I was a little bit confused when the reason I paused, so like, that's not what we have here, but it's because we used a different equation there. That's why. So there we go. There's your second piece. Yay, us.